How are you doing today, leaders? Fine. How many of you have managed to submit the assignment? That's actually great. If you happened to not submit the assignment yesterday's assignment, just be aware of tomorrow we'll be uploading the solutions. So I'm giving you the last chance to submit before 12 midday today, not at night, before 12. So by 1, I will close the submission. Got it? Once I upload the solutions, you won't be able to submit. I don't really care much what the excuse is. I've noticed that some students are here very much convincing. Say, when I was trying to submit, my screen, it just rotated and disappeared into the air. Those things, guys, they do happen. They do happen. I mean, I've been teaching more than 1,000 students if I were to count now. So don't you think maybe for a moment that one of the students, the previous students have said this before. Before you are about to convince someone, first you have to convince yourself. So that if it happens that I have some time, I really do have time, I'll go to the IT and check, did that really happen or are you corrected? I'm not going to find something that is going to say what you are saying might not be true. You get what I mean? And guess what? You have to try, guys, and speak the truth most of the time, because once that happens, even if it's not me, you will have to go to a hearing. After the hearing, you might end up being expelled. This is just simple, guys. They're giving you 10 years to rethink this facility at home. And that's what actually happens. If we expel you here, you will not be accepted in any other facility. So just be careful. No, it's just a mere 10 years, don't worry about it. You can think, if you feel like I want to start a female, you can finish that in 10 years. And then at a later stage, you will be able. So please do submit the assignment before 12 today. It's still open. It was open last night. So someone will say, I couldn't submit. I know that that's not true because it was open. Even last assignment, I did the same thing. The question I always have is, was there an assignment to submit first? Because sometimes when someone is supposed to be busy writing things down, they are busy thinking of a right excuse. So was there an assignment to be submitted? So that's the question, yes ma'am? Yes, true. The issue with the assignment, when I already uploaded the solutions are there. Now, I want to talk about something. This is very short today. We're going to have a very short lesson. It's not gonna, if we manage to have time, if we have time, after finishing this, you can raise one of the topics you're not comfortable with, then we can look at it a little bit. Okay, before I do that, these are my consultation times, guys. Every day at 2, I have a meeting. Today I have a meeting at 2, supposed to end at 5. And Thursday, I have a meeting, so these meetings are always random, but they always start at 2. That's why I have this. But on Wednesday, I already have an appointment at 2 up until 5. I don't have a meeting. And also Friday, I don't have a meeting at 2 and 5. So if you think you want to use that time for yourself, you can do it. And secondly, just because you have booked an appointment today, it doesn't mean tomorrow you cannot have another appointment. We are not struggling at the same rate. So that's what is happening here. You can have an appointment today, tomorrow, and the other days, as long as you still don't get what you are actually doing. But one thing that I want you to think about today, I'm just thinking of 4 chairs, different colored chairs. This one is not just random, guys. The students I have in this class are about 400. So I was like, okay, let me just pick 4 something. So I was thinking, suppose that I give you 4 different colored chairs. chairs. Not chairs. Chairs something else. Chairs. You have 4 different colored chairs. How many different arrangements can you make if you were to place the chairs in a row?
4 factorial.
They are?
4 factorial.
What is a factorial, guys?
1 times 2 times 3 times 4.
This is going to be a nice lesson. Let me just make it very quick. This is going to be very nice. Thank you, guys. And the second question is, if I give you 3, just write down your answers, guys, fine. The answers that you were saying to me. And then the second one is, if I give you 3 chairs, how many different arrangements can you make out of 3 different colored chairs? Thank you. And then, if I give you 2 chairs, different colored chairs, I place them here. Someone goes outside and say, arrange these chairs. And they go out and then they come back. They go out again and they come back. How many different arrangements do you think these people can see? Or how many different arrangements can you make with 2 chairs? Okay. If I give you 1 chair, it has 1 color, I place it down here, it's just standing here. Someone goes outside, you have to keep arranging this 1 chair. How many different arrangements can you make? It is. Where did the factorial go now? It just disappeared into thin air.
It's just 1 percent.
Okay. Now, I'm giving you 0 chairs, and I'm saying, make some arrangements here. How many different arrangements can you make?
0.
So, if you are saying this is 0, which means that if I'm saying make some arrangements here, and someone goes outside, you make the arrangement, they come here. If you are saying that they will see nothing, they're not going to see anything. Okay, so you're saying the arrangement is? How many of you are saying 0? Raise your hand. Fine. She's saying this hand thing is a problem. I don't want to commit to saying that I don't know this thing. I want to die not knowing, or knowing. I want to die alone. And actually, that's actually what is interesting. In the past, guys don't really consult. That's one thing that I've realized. Guys, they don't usually consult. They don't consult a doctor. If they're dying, they want to die in peace. If they're at school, they don't want to consult for it. They're like, no, I'm not going there. I will see what I can do. That's what guys usually do. I don't know why. Because I was doing the same thing. That's why. Until I was failing solid state physics, and then I had to get out of the cocoon. Like, hey, what can I do now? I don't understand this back. All I would think of is tears back. But we're actually doing something that was interesting, so I was forced to consult. Consultation is a need, it's a strategy for you to study. You don't consult because you think, I think I'm a little bit dumb. No, you're not dumb. You're just not understanding something, or it's not coming the way you're processing things. That's why you consult. Right. And studying for this course is easy. You just take 25 minutes, read through the slides. If you don't understand the slides, you go to the lesson that I will usually post on our channel. If you feel that is too much for you, you check the textbook. If you check the textbook, you still don't get it, you are comfortable with your tutors, you ask the tutors. If your tutors still, I don't get it, you book a consultation. That's very easy. You don't start with the textbook because you will fall behind. You start with the slides. There's a lot that we're going to cover. Even compared to someone who's majoring with maths, what we're going to cover is way more because we're covering so much work in 6 months. You get it? You are not mathematicians, applied mathematicians, pure mathematicians. You just need maths to excel in your careers. That is why your work is so much compared to other students. You're getting it? And you will feel like it's a lot. And you have to make a choice now because it's going to be too late, especially for test 1. Okay, let's go back to the lesson. I said that I give you 4 chairs, and these chairs here, they have different colors, like this, and that one, and that one, and then that one there. And then I said that I'm just going to use different colors here. The first one is going to be a little bit green. The second one, the second one is going to be a little bit nicer. And then this one here, I want it to be a little bit cutish. Oh, the last one is white. Okay, we'll leave this one as a white. And now I am asking you that how many different arrangements, in other words, I have a row of 4 chairs. How many different arrangements can you make? The question you should be asking yourself is, because I have to place a chair here, right? How many choices do I have? I have 4 there. So for this one, I have 4. I can either choose this one, or that one, or that one, or that one. Now, once one of the chairs have been placed, how many chairs are left? Now, how many choices do I have for the second one? So I'm going to have 3 there. Are you getting it? Now, when one chair is also gone, how many chairs are left? I have 2. Now, how many choices do I have for the third one? So you're going to have 2. And then when that one is gone, how many chairs are left? So you end up having a 1, right? Because once I pick one chair and then I place it there, I still have 3 other chairs that needs to be placed. Are you getting it? And also, once I have picked one chair, then I place it aside. There are several options that are left for the second one. Are you getting it? So I can have this chair, one chair, right? And then the second one can either be this color, or that color, or that color, or that color. In other words, this first chair have 3 other options to be mapped with. Are you getting it? Yes. That is why you end up saying, okay, if one chair have 3 other options, what will happen if I have 4? This will have its 3, this one will have its 3, this one will have its 3. That is why you end up multiplying these things. You getting it? Now, if you have 3, the same thing is going to happen. You getting it? So what I'm going to do, I'm just going to take this out. I'm just going to take this whole thing out. And then now we have 3 chairs, right? And this is one chair. This one is like that. And then I'm going to change this one to a black child. Yeah, like myself. I'm black, guys, right? Am I not black? I thought I'm black. Oh, now today you are seeing something. Yesterday I was saying guys cannot see any color. They just say, this one. It's just a moving thing. They cannot see any color. Today you are claiming that I'm not black. How do I look? Am I white? Am I yellow?
You are proud?
I'm brown. I'm not orange. I'm not green. Oh, okay. So we have these chairs. Now we want to place these in a row, right? Right. So we say that. How many choices do we have for the first one? How many choices for the second one? How many choices? So you multiply these things out and then you will end up having a 6. Do you get it? Okay. Let's try now a different problem. We have 2 now. Right. If I have 2 chairs, right, I place them here. You getting it? And then you are outside. I say, come in. Check the arrangement. Right. You're going to see something, right? You're going to see something. I get it? Yes. And then I say, go outside, and then I switch these 2 chairs around. When you're coming back, are you going to see the same thing that you were seeing before? So you're going to see something different. Okay. How many things have you seen so far? 2. And then I say, go outside, right? And then you come back in, I flip these chairs again, twice, I flip them twice. When you're coming back, are you going to see something that you've seen before, something different? So which means the maximum number of arrangements that you can have is 2. Thank you. So you keep flipping them. So for the first one you have 2, the second one you have a 1, and then this is just a 2. Now I am giving you one chair. I place my chair here, just in front of me. I say, go outside. You go outside. And then I just try and swap the number of chairs that are in front of me. Right. And then you come in, you check. You're going to see something, right? Let's start there. Okay. After you have seen something, I say, go outside again. And then I say, I'm going to switch these things around. And then I say, come in. What are you going to see? The same thing, because I have one chair. So this one, there is only one chair there. Are you getting it? Now, I'm saying to you, go outside. I want to arrange some chairs here. Right? And then I stand here. I don't have any chair now. The chairs are supposed to be arranged in front of me. You get it? And then I say, I flip some chairs in front of me, which is, there's no chair. And then I say, come in. Can you check my arrangement? What are you going to see? You're just going to see nothing, right? And then I say, okay, go outside. I want to arrange the chairs again. You getting it? And then you go outside. I press a button there. I wanted to arrange my chairs there. I arrange them, which is nothing. And then I say, come in back here. And then what are you going to see? So every time you are going outside, you're going to come back and see one thing, which is nothing. Are you saying that? Are you getting this? You're always going to see that one thing, which is nothing. So how many arrangements have I made? No. There is one arrangement that you are seeing there, which is nothing. Every time you are going outside, you come there, you see, okay, there is nothing. Right. And then I switch some chairs. I say, go outside, and then I do the same thing. So you keep seeing one thing. I'm getting it, which is nothing. It's the same thing that you are seeing, which is nothing. You're getting it? That is why when you have 0 chairs, there's only one option, which is 1, nothing. So you have one arrangement that can be made. Can you see that? That's just a little bit of what I wanted to talk about today. Did you get it a little bit? That you are saying one thing which is nothing. Okay. We're not going to do much steps. It's just, you just need this little part, guys. If you understand this little part, we are good to go. Okay. Now that you have this, these are the number of arrangements, right? And then if you say, I give you some integer, positive integer or 0, and then I say, I want you to give me a factorial of that. I am actually saying to you, how many arrangements can you make with n objects, or with 0 objects, or with 1 object? That's the meaning of a factorial. You get it? Yes. It's not only the fact that you are saying n minus 1, all those things. No. It has the arrangements attached to it. Do you get it? That's the meaning of a factorial thing. Do you get the factorial that factorial of 4? 4 factorial is the same as 4 times 3 times 2 times 1. Okay, thank you. Now, once you have this nice factorial thing, we define a constant. It's just, for now, it's just a constant, such that I take 1 over 0 factorial plus 1 over 1 factorial up to infinity, and then I sum those things. That's what that number is, right? Just for you to know that there is that number E, which is that. I want you to know that. It is defined like that, this number. You're not going to prove it, that it is equal to that. It's just, I'm saying to you, take it as just a definition I'm giving to you for free. You have to know that that number is that. And secondly, what I also want you to figure out is that this number here It's not a rational number, it is an irrational number. Right. And then secondly, this number that we have there, if I want to approximate it with a couple of decimals, it looks like this. I'm approximating it because those numbers, they continue. They keep continuing because you can see that I'm summing all the factorials up until I arrive to infinity. Are you getting it? The very biggest number there is. So that's the definition of that. Can you see that it is approximate to that number? That's what I want you to see. Approximate to 2 comma something. Do you understand that it is an irrational number? You don't get that part. Okay. What is a rational number? A rational number is a yeah.
5, 4, 5, 4, 5, 4, 5, 4, right? 5, 5, 5, 5.
Yeah. I see it. A rational number is a real number that can be written in a fractional form with both the numerator and denominator integers such that the denominator is not equal to 0. That's the definition of a rational number. An irrational number is a real number that cannot be written in a fractional form with both numerator and denominator integers such that the denominator is not equal to 0. That's the difference. Now, if I give you decimals, right, I give you a decimal number such that the numbers after the comma are finite. In other words, they start somewhere and end somewhere. Or I have 10 numbers after the comma, I have 100 numbers, but they end at some point. You don't have to think much about that number. It is a rational number if they end at a point. You getting it? It doesn't matter if the numbers after the comma are different or are the same or they are following a particular sequence. As long as they end at some point, that number is a rational number. Do you get that? Okay, let's go to a decimal now that have non-terminating sequence. In other words, the numbers after the comma don't end. And you usually don't denote that with the 3 dots. In other words, it continues like that. You getting it? If you can see after the comma that, okay, after this one number, you have 1, 2, 3, and then 1, 2, 3, and then 1, 2, 3, a sequence of that sort. Or I have 1, 2, 3, 4, and then 1, 2, 3, 4, and then 1, 2, 3, 4. In other words, you have a certain pattern that is happening after the comma. It doesn't matter if they go to infinity of that, it goes forever. That number, that decimal is a rational number. You getting it? But now, once you have a decimal number that have all the numbers randomly happening after the comma and they keep going until to infinity, in other words, they don't end, that's an irrational number. That's the difference between the two. If the decimal ends somewhere, it just means it is a rational number. If it doesn't end, then you have to check the pattern because it can be rational or irrational. Do you get it? Yes, that's what is important. Any questions so far? Okay. Now that we have this number here, who actually came up with this idea? And what is this number actually called? There are some different people having different preferences of the name. The one that I usually use and the one that is commonly used, that number is usually said or called as Euler's number. You getting it? The one that is widely used is Euler's number. Leonard Euler had contributed a lot in maths, both in just mathematics in general and also in calculus. So that number is named after him, I would say, just as an honor of the work that he has contributed to mathematics. But others, they like to call it Laplace constant. You getting it? And then others, they like to call it the base of a natural log function or exponential function. Why? Because when it comes to modeling a population of bacteria, a population of human beings, a population of animals, let me just put it like that, most of the time we are using an exponential function to model things out. You getting it? So when we are modeling things out, instead of having all the bases that are out there, we usually try to model using this number instead as a base. You getting it? Yes. And then finally, when was this thing actually discovered? Who actually came up with this idea? This person who actually came up with this, it was this guy Bernoulli. He was studying compound interest, and then he found out some interesting things, that there is this number which is actually can be represented or seen as a limit sense. Take a note of this. The person who had discovered this number was Bernoulli, but it was named by someone else. You getting it? So it's not Bernoulli's number or anything, but he discovered it. You getting it? And the reason this number is so-called Euler's number is because of so many discoveries. I can only name, I think, one, whereby you have e to the exponents I times theta or x. And he discovered that this is the same as cosine of theta plus I sine of theta. So these are some of the information that actually he came around with. That's why he was given this honor. Again, it up to this part. And once you have this, why this number is important, I'll give you one important thing that you have to take down out of this. Because I can see some of you like, do I have to write this in the exam? Is it coming in the test? Is it not coming? Guys, every day when we have a lesson, I'm trying to give you a little bit so that you can have a starting point to investigate. You getting it? Why am I doing that? In this class, every single year, there are students who end up deciding, I'm not going to continue in pharmacy now, moving that route of maths. I don't want you to go that side and you are blank. That's why I usually do this. Not everything that I'm saying is going to come up in the exam. You getting it? Yes. Why is this important, this number? I've told you that it has to do with an exponential, and exponential is usually used to model things. But the most important thing, there are two important things which affects us here in this class. We're going to prove them next time. The area under the curve of the hyperbolic function 1 over x. If you start at this portion here, you see this portion that I have here, from 1 up to e. If I'm starting here up to some e, this area under the curve is just equal to 1. You getting it? And then the second thing is simply that if I give you an exponential function, and you can see the exponential function is going all the way up. Let's say I give you an exponential function of e to the power x. It's going all the way up. And now, I want to find out what is the change or the slope of the tangent line that is touching that curve at one point. It doesn't matter which point, but I just selected this point or that point or any point. What will be the gradient? I think you know the gradient. Gradient and the slope is one and the same thing. What will be the gradient of that function? It turns out that the gradient is the same as e to the power x. You getting it? In other words, the derivative of e to the power x is still the same. So that is why it is so important. It's because, one, it is one of the natural mathematical constants. Are you getting it up to this one? Now, okay, I will get back to that. What is important for you is this. Do you realize that this number e is important? It's special. You don't realize that. You don't realize that it was started by so many people. This one discovered it, and this was given to this person. Can you say that? Only that. Okay. Do you know the value of that that number? Do you know the value of that number? Can you punch it in your calculator in? You don't have a calculator, thank you. Which means I don't even have to think about this calculator issue for the test. Thank you guys. What is important here is that this number here is like this if you are approximating it. That's what I wanted you to find out. The number E is important. That's what is important. The number E is important. Everything is a theoretical sense. If you're coming in the exam, not directly. We are not usually examining history of things here. We usually wanting, can you do this? If I'm talking about radians and degrees, can you convert radians to degrees? That's it, right? And then the second thing is, if I'm giving you 2 to the power x, can you convert it to some e, let me say times k to the power x? That's what is important for you. We're going to do that, not what we didn't do today. So that's what we are going with this, because when it comes to mathematical modeling, that number, it always comes out to model the exponential stuff. You get it? So that's what is important for you. You don't have to stress about this whole thing. Do you get it? Okay. Do you have any questions so far? You can ask any question, whether this or the previous session. Or the previous, the session before the previous, or the previous, or the previous. Which question do you have? Should I end the class here? Okay, what do you want us to talk about? Because that's what I wanted to talk about. Highlight what this number is all about. Yeah. Okay, let's look into this, guys. What are you going to say? Someone said I should touch a little bit about logarithms or logarithmic functions. This is one of the functions. The student function is because that is the inverse of x is equal to simply a couple of things. You understand? are finite. But now we can see that it is the frequency and the so these are one of the not only this, for missing why is the content why is the Let me first deal with the first question before I get expelled and lose my income. This is what is happening, guys. If let's say I have this function here, which is an exponential of this kind, y is equal to a to the power x, where a is greater than 1, it looks like this, right? Now, how does the inverse of that function look like? Or how do you find the inverse of that? First, you draw the line y is equal to x. Are you getting it? So you're going to have your line there, which is y is equal to x. Do you get it? And then, when you are standing above that line, what will you see in the mirror? That's the question. Right? Do you see? Can you see something? If let's say you are standing up here and then you are looking at this line is the mirror, guys. What will you see in the mirror? First of all, this graph will cut at that point when y is equal to 1. Where will that 1 be? Yes. What is basically happening here? When you are standing at that point, this side, which is the y-axis, will become the x-axis. You getting it? So that line in the mirror, you go all the way down, it will become that line. So that one will be there. Are you getting it? And then secondly, this side here, if you look for this function here, which is y is equal to ax, it is a horizontal asymptote, which means the curve will not touch it. Do you get it? Yes. Now that that has happened, when you are looking into the mirror, this horizontal asymptote will become a vertical asymptote. Do you get it? Which means that the inverse of this function will not touch the y-axis. So it's going to go like this. Do you get it? And then, now that you have that part there, we had y is equal to a to the power x. When you're interchanging x and y, what will you end up having? You're going to have x is equal to a to power y. That's the inverse. You get it at that point? Okay. Let me go back a little bit. Do you get the shape? Okay. Guys, this is the mirror, it's sitting like this, and then I'm looking into it. I have a curve that is going like this in the mirror. What will I see in the mirror? It has to be going like that. That's the meaning of that. I'm not coming up with my own things here. If I'm coming with my own things, please tell me. Okay. Now I am saying the inverse, the meaning of an inverse, it means that you are interchanging x and y. That's the meaning of having. You getting it? So you have this. Now that you have this nice thing here, we have an exponent which is y, and we always want to make y a subject of the formula. That's when we actually rewrite this in a form that will make y the subject of the formula. But it is the same thing. You're getting it a little bit? Yes. So this thing here, when you want to rewrite it, I'm gonna clean this whole thing up because I only have this space, guys. I don't have another space. And I only have 3 minutes left. I said you have X. This is X, guys. X for Dr. Kand. Yeah. That is why you're studying X's in grade 12. They are trying to honor me. Yeah. But here's the thing, guys. You have X here, which is equal to A to the power Y. Now, you want to rewrite that. So I always say this, when you want to rewrite this whole thing, you must always realize that X is just a number, guys. It's not special, it's just a number. And I also want you to know that A is a base. And then Y is an exponent. So this thing of logarithms is just in a rewrite. So we are redefining a function that will say the very same thing that X is equal to A to the power Y. And what this thing says is that whenever you have something of this kind, this thing is the same or equivalent to saying I have an exponent, right? And this exponent is the same as this log function. And you have a base that is written down there, and then you have an X there. So this thing here and this thing here, they mean the same thing, is one and the same thing. You getting it? Yes. So how can we change this now and write it in this form? Y is equal to log so you're going to have Y is equal to log AX. That's the meaning of this thing. This thing and that thing, they mean the same thing. It just means the inverse of the exponential function. That's all there is to it. You're getting it a little bit. Yes. It's not that hard. It's just basics, guys. It's not.